I'm a physicist, and some people ask me the question, what has physics done for me lately? Do I get better color television? Do I get better internet reception with physics? And the answer is yes. If you want to understand the future, you have to understand physics.
T-minus 90 seconds and counting. All
Hi everyone, my name is Yusra.
And I'm Sibel.
We are the freshman students at AGÜ, and today we will explain the physics of billiards.
We prepared some extreme shots to discuss how effective physics in billiards, and I hope you will enjoy and learn something. Let's go. Billiard balls deform very little when they collide, and they quickly spring back from any deformation they do undergo. Hence, the force of interaction between the balls is almost perfectly conservative, and the collision is almost perfectly elastic. Elastic collisions occur when the forces between the colliding bodies are conservative. When two billiard balls collide, they squash a little near the surface of contact, but then they spring back. Some of kinetic energy is stored temporarily as elastic potential energy, but at the end, it's reconverted to kinetic energy. In this example, we assume that cue ball and green ball is constant after the collision. Now we can say that it's a two-dimensional collision. First of all, since we know that the collision is elastic, the mechanical energy is constant. We also assume that there are no external forces acting, so the momentum is constant. The collision is two-dimensional, so the change in each component of the momentum is zero due to collisions. A certain kinetic energy was generated because the white ball accelerated before it collided. Later, when it hit the green ball, it's an elastic collision, so the energy transferred to the green ball, so the white ball stops. The green ball also gained energy and hit the purple and red ball. When we look at this part only, because it's an elastic collision, the force momentum belongs only to the green, because the masses of purple and red balls are equal. When we look at the other example, you see that the cue ball hits the forward ball by jumping on another ball. In contrary, we discussed previous case, this is a one-dimensional elastic collision, in which all the velocities lie along the same line. We choose this line to be the x-axis. Each momentum and velocity then has only an x component. From conservation of kinetic energy, first we have the kinetic energy of cue ball, which is equal to final kinetic energy of the second ball. And because of the initial momentum of second ball is zero due to its in rest, the total initial momentum is just of the cue ball momentum. Again, in real life, there are some of external forces like friction, air conditions, some calculations that we made theoretically cannot match with real life basis.
Newton's first and second law explain the relationship between object and the force acting upon it. According to Newton's first law, if the net force acting on an object is zero, that object maintains its state of rest or constant. Newton's second law says that if the external net force on an object is not zero, the object accelerates in the direction of the net force. Now we can see the free body diagram of a billiard ball, which stays at rest. The gravitational force and the normal force exerted on it have the same magnitude but opposite direction, which come out with zero net force. Only if the stick applies an internal force on the billiard ball, the ball will take stationary position on the horizontal level. It is the product of the mass of an object and its velocity. In billiard game, all the balls have the same mass, so that the velocity is a determinant of the motion. Impulse is defined as the product of average force multiplied by the time it's exerted. The billiard game is about collisions between the cue ball and other balls. It's moved in the required direction to reach the target hole. Here the example. The concept being applied here, including elastic collision and conservation of momentum, can also be found in the game of billiards. The two balls are stationary rest on the table. The red ball and the white ball has the same mass. Before the collision, the white ball has the constant velocity, and the red ball is at rest. After the collision, the white ball stays at rest, but the red ball moves with same direction and velocity as the white ball has before collision. Then we can say the momentum is conserved. We mean that both the magnitude and the direction of the momentum not changed. Here another example. This also applies to collisions in two dimensions, since momentum is a vector quantity. We can resolve into x and y component in order to conserve all momentum. The x component of momentum should be the same before and after the collision, and the y component must be the same before and after as well. As a result, the ball will move with a certain direction and speed, depending on the speed of the cue ball and the angle which they collect. Is the same, every part of life has its own physics rules, and today we try to present just a little part of it.
That's all. Thanks for watching and don't forget to like and comment our video. See you.